So, I made another 3D renderer in Factorio, and now I have to try and explain this one. But first the specs for the new design. It can render an arbitrary number of perspective projected texture mapped triangles to a 64 by 32 8-color screen at a rate of 1 triangle per tick, plus an overhead of about 2 ticks per completed frame. The textures are all 32 by 32, and in the current design up to 4 textures are supported. Unlike the previous design, this version does have a Z buffer, which means the order that the triangles are drawn in no longer matters. Now, onto the changes to the design. I'm not going to go into as much detail as in the previous video, since this design is even more complicated than the previous one, and I don't want to get as bogged down in the specifics and the complicated maths. This version uses a perspective projection instead of an orthographic projection. This basically means that we see the scene from a sort of virtual camera in the scene instead of a kind of plan view. The perspective projection itself is handled here, though it should be noted that using a perspective projection has some effects on later parts of the design, mainly the Z-depth calculation and the texture mapping. Now we have to combine the points into triangles, which happens here. The current configuration is rendering the 12 triangles that make up the 6 sides of the cube you saw in the beginning. This is also where we add the texture data to the triangles. This uses a standard UV mapping that works the same way it would in any normal 3D software. The new design is pipelined and renders the triangles sequentially, which means we have to give it the data for one triangle at a time. Specifically, it takes the data for one triangle each tick. Now we get to the rasterizer, which I should probably just call the renderer for simplicity's sake. This is what takes the triangle data and generates the image. This first section works the same way the original did, finding where each triangle intersects each line and sorting to find the leftmost and rightmost points. What's new is that it then calculates the barocentric coordinates of those points. And if you don't know what barocentric coordinates are, don't worry, neither did I. They're basically just a set of coordinates that let us interpolate inside a triangle. So if we know the x and y coordinates of a point in a triangle, we can calculate the z coordinates and the texture coordinates of that point. So now we have the z coordinate and the texture coordinates of the leftmost and rightmost points of the triangle on this line. Well, sort of. Remember when I mentioned the perspective projection affecting the z-depth calculation and the texture mapping? Yeah, this is where that comes up. You see, the perspective projection involves dividing both x and y by a function of z, which means that the z-depth of a triangle in the perspective projected space doesn't vary linearly. Luckily, there's a fairly simple solution. We just do the interpolation to calculate the z-depth with 1 over z instead of with z, and then take 1 over the result to get the actual z-depth. If that didn't make sense to you, don't worry. I'm not entirely sure I understand it either. Anyway, we have to do something similar to calculate the correct texture coordinates, but I'm not going to go into any more detail on that. I'll try to link to a video that shows the original PlayStation's graphics, since that system didn't do the correct texture mapping and had a bunch of strange texture warping as a result. Okay, so we can calculate the z-depth and texture coordinates for the leftmost and rightmost points of the triangle on this line. For real this time. But we still need to calculate those values for each of the pixels between those points. For this we simply interpolate, still with the confusing inverse values, between those points. We then do the mapping back into actual Z and texture space, and that gives us all the needed pixel data for a single triangle. And since this design can do that repeatedly, we can do this for each triangle and get all the needed data. Now, this is where the Z buffer comes in. The Z buffer for each pixel can store the Z depth and texture data for that pixel, and each time new data comes in, it's compared to the stored data, and the Z buffer keeps whichever version has the lower Z depth, since that means the new data is closer to the camera and thus should be drawn in front of the other data. Then there's the frame buffer. This just waits until all the triangles have been rendered and then copies the result from the Z buffer. This means we only display frames once they've finished rendering, instead of drawing half-finished frames to the screen. Now we do the actual texture mapping. So far we've only been storing which texture each pixel should use and where in that texture it should get its colour from. So now we do a lookup for each pixel to find out what that maps to. And now we're done. We have the colours for each pixel ready to be drawn to the screen, which, again, I'm not going to explain as it's basically the same design as before, except I'm no longer packing data for multiple pixels into each channel, which makes wiring a bit of a pain, but means that it'll be easier to adapt if I want to connect a different screen design. Now, I thought I might discuss a few of the limitations. Currently this thing doesn't do any clipping, which means that anything that renders behind the virtual camera causes some really confusing errors. I might try to solve this with a module that would clip triangles before they're sent to be rendered, but there's a lot of potential complexity there, so I'll have to think about how to go about it. Now, textures. Currently it supports up to 4 textures, but it's easy enough to expand that to about 32 since I left room for that in the encoding, but that would require quite a lot of extra space. I might make this change, but there are other changes I want to make first. I could also make the texture resolution higher, but I think 32 by 32 is fine for now, given the screen resolution. Now, onto flicker. As you can probably tell, the resulting image from this thing flickers quite a lot. I think this has 2 main causes, one of which is the low precision that I'm using for all the calculations. The representation that I'm using gives me roughly 3 decimal places of precision, and sometimes that isn't really enough. I think this is what's causing the flicker along edges, as sometimes the low precision leaves gaps in the edges, and the triangles behind them show through. I believe the other source of the flicker is a lack of texture filtering. This is what's causing the shimmering on the faces. I don't think this is something that can be solved with an 8-color display, since you need to interpolate colors to be able to filter textures, which brings me to the display. The current display is relatively simple, but its limitations are too great, and I think it might be the main thing I need to improve to enable certain other features. Now, while the resolution isn't amazing, I think the bigger problem is color depth, or the lack of it. The current display has an effective bit depth of 3 bits, and that simply isn't sufficient for what I want to do. So I need to find a way to get higher bit depth. I have an idea for something that might be able to get me a 6-bit or 64-color screen, but we'll have to see if that idea pans out. Right, onto performance. Right now, with the build sitting idle, I get about 45 frames per second, and this drops to about 35 when the renderer is turned on. This doesn't leave a lot of room for further expansion, but I do have an idea for how to solve this. Rebuild the whole renderer again, this time with heavy use of pairwise logic. You see, most of the performance trouble comes from simply having so many combinators, about 200,000, causing entity updates, and by rebuilding with pairwise logic, I can build all the per row logic into one big unit instead of the 32 smaller units I currently have, and I can replace the 2048 copies of the per pixel logic into about 8 copies of a new design. This would massively reduce the combinator count and hopefully bring my frame rate back up to 60 FPS with some headroom for further expansion. So, I guess, future plans? Now, I might not do any of this, it depends on whether I get bored of the project, but assuming I keep going, my next steps are probably going to be something like build a new display and figure out if 6-bit color can work, rebuild the thing using pairwise logic to try and make some performance games, and add a clipping unit so that things behind the camera don't break things. So, that's the video. Thanks for watching. Bye.